Hello, welcome back. My name is Jason with mathandscience.com, and this is honestly one of the most important lessons that I've ever taught in any subject to anybody watching. It's one of the most important topics. The title is called Exponential Growth of Money, also called compound interest. You know, probably the number one question that I get from students of all ages, especially young students, is when will I ever use this algebra stuff? When will I ever use trig or calculus? When will I ever use it? I don't care about that. That's what I hear a lot. Well, this lesson is going to teach you that, because whenever you put money in the bank and earn interest, whenever you take out a loan and pay interest on the loan, what you're doing is you're kind of trusting them if you don't understand what's going on. But really what's happening is there's an exponential function that determines how much money you're going to earn in interest or how much debt you're going to pay in terms of interest on the loan. That's an exponential function. And that exponential function is very, very simple to understand, but it does take a little bit of talking about it for me to help you understand what it means. And I can tell you this, and you can probably understand this by listening to a quote from somebody you've probably heard before. His name's Albert Einstein. Einstein said the following thing: compound interest is the eighth wonder of the world. He who understands it earns it, but he who doesn't understand it pays it. And what that means is really, really important for you to understand. Compound interest governs how much money you're going to earn when you put money in the bank, or when you invest money in a retirement account, or just in the stock market to try to acquire wealth. So that compound interest is an exponential function. And we've been learning about exponential functions. You know the shape of that exponential function goes up very rapidly. So if you save money, it's the eighth wonder of the world because it gives you more and more and more money over time. But he who doesn't understand it pays it. And what that means is when you buy a house, you have a loan, and that loan acquires, you have to pay interest on that loan, and the amount of money you owe goes up and up and up, also exponentially with time. Anytime you buy a house and you take a loan for a car or a student loan for university, you have to pay interest, and that's exponential also. So it really is one of the most practical things you could possibly learn, and one of the most important lessons here. Now we're going to start off by I'm going to ask you a question, and I'm going to demonstrate powerfully why compound interest and exponential growth of money is so important. I'm going to give you two choices. For 30 days, over a month, 30 days, we're going to do the following options. I'm going to give you two options. Option A is I'm going to give you $10,000 every single day. So 10,000, 20,000, 30,000, 40,000. That's how much money you're going to earn if you choose option A. Option B is I'm going to give you 1 penny, which is 1 US cent, or you could pick some other currency. One cent, right? 1 tiny little penny on day number 1. But what I'm going to do is double that every day. So it'll be 1 cent, then the next day you get 2 cents, then I would double again and I would give you 4 cents, and so on. So what would you choose for 30 days, just for 1 month? Would you pick the $10,000 every single day, and at the end of the 30 days you would have that much money? Or would you pick to go with the 1 cent per day, and I will double that balance every day, only for 30 days though? How much money do you think we're going to have at the end of the month for each of those cases? All right, so here we go. Here's what the answer is. Here's day number 1. Choice A is I give you $10,000 a day. You start with $10,000 a day. Choice B is I give you only 1 penny. But then on day number 2, I give you another $10,000. That's how this column works, right? But choice B, I double the previous balance. I double that and I give you 2 cents. All right, now we go to day 3. Obviously, every day you go down this column, it goes 10,000, 20,000, 30,000, all the way down to $100,000 at the end of 10 days. Choice B, I keep doubling it. 1 cent, then 2 cents, 4 cents, 8 cents, then 16 cents. You see right here, you'd have $50,000 and only 16 cents in this column. But let's keep on going. If you keep doubling, you get 32 cents, 64 cents, $1.28, $2.56, $5.12. In this column, you would have $100,000. So if you were going to stop this at 10 days, you would obviously want to take the $10,000 a day, but let's keep going. All right, what's going to happen on day number 11? I'm going to have $110,000, but I doubled that $5.12 over here to get $10.24. Now in this column, I keep going down 10,000 a day, but in this column, I go from $10.24, $20.48, $40.96, $81.92, $163.84, $327.68, $655.36, $1,310.72, $2,621, and 44, and then 5,242 and 88 cents. Still, in this column, I would have $200,000 compared to only about $5,000 after day 20. So obviously, if you were going to go only to 20 days, you would want to take the column A to get your 10,000 a day. Let's see what happens when we go into the tail end of the month here. Here's where we start seeing some interesting things going on. Day 21, I have $210,000 here, but in this column, I've doubled that $5,000 to $10,485. And then I've doubled again to $20,000 and some change, $41,000 and some change, $83,000 and some change, $167,000 and some change compared to the $250,000 I would have here. Here in red is where the right-hand column starts to beat the other column. So actually, if you run this thing out to 30 days, what's going to happen is you're going to run through 300,000, 335,000, then 671,000. Here's where you hit $1 million on day 28. $1,342,177.28 on day 28 as compared to just simply $280,000. We double that, we get $2,684,354 and some change. And on day 30, we double that again to $5,368,709.12 because compared to $300,000. It's incredible. And it comes about because the right-hand column, it isn't really obvious when you first look at it, but the column where I'm doubling every day is actually an exponential growth of money. Even though it doesn't really seem like it at first, it seems like, oh, who cares? 1 cent, 2 cent, 4 cent, whatever. I don't care about that. But really, when you get down to a certain critical number of days in the future, you overtake the linear function. This is a linear function because I'm gaining the same amount of dollars every day, 10,000, 10,000, 10,000. So this is a linear growth of money. If I graph it, days versus dollars, it's just going to be a straight line because I'm gaining a constant number of dollars every day. But this column, notice what's happening. What I did is I took the 1 cent, and on the first day I multiplied by 2 to get 2 cents. And then the next day after that I multiplied by 2 again. And then the next day after that, I multiply by 2 again and 2 again. So if you get a calculator and actually just do it, put in 1 cent and then hit times 2, times 2, times 2, times 2, then you're going to get all of these numbers in this column. This is not rocket science, what's happening in the right. Just times 2 every day. And you do that 29 times because on day 1, the first doubling, when I multiply by 2, this was one doubling, then this was another doubling, and so on. So even though there's 30 days, there's actually 29 doubling periods. And so if you multiply by 2 29 times, you will get the $5 million answer, okay? So in terms of, when you look at what you have here, it's 1 cent times 2 times 2 times 2 times 2, 29 twos. What does this look like? This looks like an exponential here. 2 to the power of however many days I doubled. Because remember, what an exponent is when you multiply by itself. So I'm taking the first number, I'm multiplying by 2, which means I have 2 raised to the 29th power. So if you don't want to do the times 2 deal in your calculator, just grab a calculator, take 2, raise it to the power of 29, because that's how many doubling periods we had, and you take the answer and multiply by 1 cent. You will get 5,368,709.12. And if you were to plot the money that you get as a function of the days in comparison to the linear, it's going to look exactly like an exponential function. In the beginning here, it grows very slowly, which is what we saw. But then once it hits a critical value, it starts to take off. And in those last, 1, 2, 3, 4, 5 days of the month is when you earn incredible amounts of money. So what does this mean? Okay, it doesn't mean I'm trying to teach everybody to be greedy. It's just that the number one question I get in math is, what is math useful for? Why do I care about math? When am I ever going to learn and use math in everyday life? That's what I get all the time. And here is your most practical benefit and use of math in everyday life. Is your growth of money and your growth of debt is governed by an exponential function called compound interest. Now this was a crazy compound interest just for illustration purposes, but what I want to do now is I want to give you a more practical example to show you what the growth of money does over a realistic time period with a realistic interest rate. And you will see this nice, beautiful exponential function. And then I want to go dive more into the math, and I want to solve a couple of problems and really show you what the formula is for compound interest and where it comes from, and also that you will then know and see that it is an exponential function. Anytime you have an exponential function, you will always beat a linear function. no matter what, as long as you give it enough time. So let's go off and do the computer demo. We're going to do a computer demo here where I'm going to show you what's going to happen to a growth of money. Let's pick an interest rate, 8% interest. Let's look over a period of time of, let's say, 40 years. Let's say you start working around 20 years old, and then you go until you're about 40 more years. It's about 60 years old when most people start to retire. Let's see how much money you'll have if you start saving early a small amount of money with compound exponential growth of money in the form of interest. Hello, welcome back. So here is a website. It's a US government website called investor.gov. It's free. Just go to investor.gov. You can do everything I'm about to show you here. What we're going to do is look at a realistic example of saving money, okay? You have an initial investment. Let's say that you're 20 years old, you have your first, good job, and you start to try to save some money. Let's say you start this account with $100 or 100, whatever currency that you have in your country. Let's say $100. And let's say every month you take your paycheck and you save $100 out of your paycheck. Now you might say $100 is a lot of money, and it is a lot of money, but $100 is something like, a few dollars a day. It's like let's say $3 a day. There's 30 days in a month. That's like $3 a day, a little over $3 a day. It's like a coffee. Stop getting your coffee, once a day. All right. And so you save $100 a day. Now let's take a look from 20 years till most people retire at around 60 years old. So let's say that you save this and you do this every single month for 40 years. And your interest rate, let's take a look at and calculate it for an 8% interest rate. Now, when you look at the U.S. stock market over the last 30 or 40 years, you've averaged about 7 to 8%. So, you may or may not agree with this number, but we're going to calculate based on 8%, and that's pretty realistic based on history, okay? That's all you got to do. You have an initial amount of money, how much money you're going to put in every month, how many years you're going to save it for, and what is the interest rate. And we're going to compound it annually. That means we're going to get 8% free money, that's the interest, every single year on the money that we're putting in. Let's calculate and see what the results are. All right, let's take a look. Here is what the graph looks like. All right, you can see here on year 0, we saved $100, and the next year we actually saved and we contributed $1,300. We got a little bit of free money from the interest at $1,308 there. You can see what's happening though. As you go off and off and off into the years, the red curve is pulling away exponentially from the green curve. The green curve down here is the money that I'm putting in every month into that account, the $100. This green number is only the money I'm putting in for my paycheck. The red money is all basically the free money I'm getting. It's the total value of the growth of that money over time. So you can see after year 40, how much money do I have? I have $313,040 in this account, but I only actually put in $48,100. So I earned something like $260,000 totally, completely for free. But you see, in order to do that, there was many years here in the beginning where I didn't earn very much money. But after some critical amount of time, it starts to pull away and starts to go exponential on you. All right, now $100 a month is, real money you have to save. I agree with you. But whenever you get, you go to university, you get a good job, I think it's perfectly possible for most people to save around $350 a month. You might say that's impossible for me. Well, maybe it is, but $350 is what a new car cost. So instead of getting a new car and paying that monthly fee in a new car, maybe you get a used car, or maybe you just drive your car for a much longer period of time. And instead of buying that new car, you take that money and you put it into this account. Let's see what would happen over 40 years. We start out with $100. We save $350 every month for 40 years at this exact same interest rate. Let's recalculate it. And what I have at the end of 40 years is now, instead of $300,000, it comes out to $1,090,209. But the amazing thing is, look at how much money I put in. I only put in $168,100. So I saved that $350 every month, and yes, it was a challenge to save that money, but I put in $168,000, but I got basically $850,000 for free by doing that. This red curve is the exponential growth curve of all the free money that has come into my pocket by saving early and saving as much as I possibly could. And then, the green line is just the money that I've put in. Now, I know probably some of you are curious, so let's go ahead and do something probably at the upper end of what some people can do. Let's say you could save $500 a month. If you're married, you both have a job, you save some money, and after say $500 a month, and you recalculate that. At the end of that 40 years, you're going to have 1,556,000. So we can play this game all day. I don't want to continue playing this game. I want you to go to investor.gov and type these numbers in here. The point is maybe you can save 500, maybe you can't. Maybe you can only save $50 a month. All right, let's see what happens if you save $50 a month. What do you get at the end of that? At the end of 40 years, I only put in $24,100, but this account is worth $157,600 by saving $50 a month. That's something like $2 a day, $1.80 a day or something like that to save that much money. This is the power of compound interest. It's the power of the exponential function, and you can see that it does look like an exponential function. So what I want to do now is go back to the board and dive into where this curve comes from and how to solve problems that deal with compound interest. All right, I hope you've enjoyed the computer demo and understand that the shape of the curve when you invest money at some sort of annual interest rate actually follows an exponential curve. Now, why does it follow an exponential curve? That's what we want to talk about now. Why is it an exponential function? In words, in a nutshell, this is the reason why. Let's say you start on day one with some money, $100. On day number two, let's say you earn some interest, very small amount, let's say 8%. So now I have more money than I did on day one because I earned a little bit of money. But on day three, I again earn, let's say, another 8%, okay? But that 8% is calculated based on what I had on day two. So every time you compound, that's what it's called when you calculate the amount of money you get, it's called compounding, right? So when you calculate the new amount of money I have, it's always based on the previous amount I had. So I started with some number, I gained a little bit, but when I calculate the next amount of money, it's a percentage of what I have on day number two, which is already more money than day one. So now I have even more money. But then the next time I calculate the interest, I calculate it based on the latest balance, which is even more money. So you see what's happening is every day I'm earning more money, or every year I'm earning more money, and I'm calculating the free money I'm getting based on the amount of money I had the previous period, which also had free money. So every day I'm gaining money, and I'm calculating the amount of free money I'm getting based on the free money I had yesterday. So it snowballs, and it kind of gets out of control, and that's why it goes up like that. So we have to define some terms. The money that you start with is called the principal. That's how much money I start on day number one. So I'm going to write a few terms down, and we're going to talk and derive specifically why this thing is an exponential function. So the principal, that's just how much money I start with. Let's say I start with $1,000 and I'm going to put it in the bank and I'm going to earn some interest on it. So this is the initial investment. It's just how much money I put in myself, okay? And let's say that I earn 8% interest. Now we have to talk about something else, which is called, let's say that it's compounded annually. Whoops. Annually. You're going to start to see something where it talks about compounding annually or compounding quarterly or other kinds of compounding. Don't get so worried about it. Compounded annually just means that's when the free money comes in. It's every year. So every year I get 8%. And then the next year I get 8% of what I had from the previous year. And then the next year I get 8% of what I then have on my most latest balance. So I'm growing every year, but I'm gaining 8% on the latest balance in my account. So the compounded annually means that's happening every year, one time per year. That's all that means, okay? So how would we calculate how much money I actually have in the bank if I invest some amount called the principal, initial investment, but let's just pretend just for this example that it earns 8% compounded every single year, which means annually. Okay, so what we have then is the value at end of the year is going to equal the following thing. It's going to be, let me write it all down, then I'll explain it to you. It's going to be 1 times the value at beginning of year okay, plus it's going to be 0.08 of the value at the beginning of year. All right, so basically what happens is every year I earn 8%, but I still have the initial investment I put in. I still have the principal. So what happens is the money I have at the end of year number 1 is 1 times the principal. The value at the beginning of the year is just my principal. It's 1 times that. That's just the principal value. But I'm going to add to that 8%. Now, when you deal with percentages in math, you never ever write a percent symbol. You just convert the percent to a decimal. So 8% as a decimal just means you move the decimal point 2 spots, because remember, percent means per 100, so you're dividing by 100. So this 8% means it's 0.08. So you're adding to my initial amount of money, you're adding to it, this is the free money, 0.08 times the principal, which is the value at the beginning of the year. Okay, so if I want to kind of write this a little bit neatly, then I would say value at, I'm going to call this end of year. This is EOY, end of year, is going to then be equal to 1.08 times value at the beginning of the year. If I can write the word at. Okay, beginning of year, end of year. So what's happening here? The value at the end of year 1 is 1.08. A lot of students wonder where the 1.08 comes from. All this means, 1.08, remember, is just simply 1 plus 0.08. That's what that means. So 1 plus 0.08. So the reason we multiply by 1.08 is because the 1 means the 1 times this is this number. That means that's how much money I started with. The 0.08 is the free money. Again, that's times this. So you can look at this as algebra and you can factor out the value at the beginning of the year, pull it out, and then you're going to basically be able to add these together, and it's going to be 1.08. So the actual free money is just 0.08 times my initial investment, but I can add to that what I started with. So ultimately, the number you're multiplying by is 1.08. This is going to be the amount of money I have at the very beginning of year number 2. All right. So a chart is worth 1,000 words. All right. So I think it's very, very important that we write a chart. So here is the time in years. This is compounded annually. So this calculation of getting the free money, it's only happening, every single year, right? So let's say that I'm at the beginning of the year, at the year 0, right? And then I have year number 1, year number 2, year number 3, and I'll go on after that in just a second and show you what that is. But basically, this is year number 1, year number 2, year number 3. What is this calculation going to look like? Okay, so this is going to be the value in dollars. All right, so what's the value in year 0 at the beginning, so to speak? It's just going to be whatever the principal is, whatever that number is. Let's pretend that we've invested $1,000, okay? So let's say that this number is actually $1,000. That's what I start with. What is going to happen at the kind of the beginning of the next year after 1 year has passed? Well, what's going to happen is I'm going to take this principal and I'm going to multiply it by 1.08. The 1 means that I'm kind of carrying over what I started with, but the 0.08 is the free money I'm getting there. So ultimately, I multiply by 1.08. So what do I have here? I have the principal times 1.08. That's how much money I'm going to earn. So if I started with $1,000 and I multiply by 1.08, I'm going to get a number 1080. So at the end of year, at the beginning of the next year, once the first year has happened, I no longer have $1,000 in the bank. I have $1,080 in the bank. The 1,000 is the money I started with, and the $80 is the free money, right? 0.08 times 1,000 is 80. So the free money is the 80, and I add them together, and I get $1,080. Okay, what is going to happen at the beginning of the next year? Well, I'm going to take this balance, the $1,080, and I'm going to multiply it again by 1.08 because the next year I earn again 8% interest, and I can still keep what I had started with there to begin with. So that's going to come out to 1166 decimal 40. So 1,166 decimal 40 on $1,000. Now, in terms of math, what's going to happen is you're going to take that principal, you're going to multiply it by 1.08, but then you're going to take and you're multiplying this by 1.08. So I take this and multiply by 1.08. So what I have is 1.08 squared. okay? Because what's happening is between this step and this step, I multiply by 1.08. But between this step and this step, I again multiply by 1.08. So this is times 1.08, and that's why it's squared right here. So what do you think is going to happen over here? Well, I'm going to have, for on year number 3, I'm going to have 1.08. It's going to be cubed. Why is it going to be cubed? Because what I do is I take the amount of money I had in year number 2, and again, I multiply by 1.08. So every year you're multiplying by 1.08. And if you're going to do this kind of pretend on $1,000, I would take this number and multiply by 1.08, and I would have 1259.70. I could be rounding here, so the exact number may be not quite right, but you see I started with 1,000, then I went to 1080, then I went to 1166, then I went to 1259. And so I continue this process every year. On the end of the first year, I multiply by 1.08, I get some number. Then the next year, I multiply by 1.08, I get some number. And then the next year, I multiply by 1.08, I get some number. Just like we were multiplying by 2s over and over and over again for that ridiculous example where I was giving you so much free money, it's crazy, before. This is a much more realistic thing. But notice what's happening. It's p times 1.08. But in year number 2, because you multiply by 1.08 again, it's really p times 1.08 squared because it's multiplied 2 times. Then the next year, it's p times 1.08 cubed, 1, 2, 3, because I'm multiplying it again 3 times because I'm taking the previous number and multiplying it again there. So what is going to happen if I extend to year number 4? Then it's going to be p times 1.08 to the 4th power. Year number 5, p times 1.08 to the 5th power, and so on. So instead of going in there and talking about year number 4 and year number 5, let's go down the road to year number t. Let's generalize it to year number t. So then this is going to be p times 1.08, not to the 4th, not to the 5th, not to the 6th. We're generalizing it, so it's going to be to the tth power. That's what that means. Because every year you're multiplying by 1.08, so the exponent goes up and up and up. And look at what this is. P times 1.08 to the power of t. That is an exponential function. Remember, exponential functions have the variable in the exponent. That's what it means. The time in years is a variable that is now in the exponent here. That is why compound interest is an exponential function. That is why it grows so rapidly like these exponential functions that we have been studying. Okay? Now, one more definition I want to give you before we go on to the next board is for this example, we were saying that we earned 8% interest compounded annually. Okay? So what this means, the actual term that you're going to see in your problems, this is called an annual interest rate. It's an interest rate because it's the percentage you multiply by, and it's annual because it means you do it every year. Every year I get another 8%. Every year I get another 8%, and so on. All right, so we want to talk about this in the most general form. So what this means is that if I'm compounding annually like this, the amount of money I'm going to get, this is called the amount of money I'm going to have, it's going to be equal to the principal, however much money I put into this thing, times, in this example, 8%. The 1.08 means I'm multiplying by the full balance of what I had before plus 8% free money to the power of t. So it's really important to study this. This t is time in years, right? This is called the interest rate. Specifically, the 0.08 part of it is the interest rate. The p is called the principal. And the a is called the amount. That's the amount of money I'm going to have total. So I can do this as an annual compounding where I get 5% a year, 5% a year, 5% a year, over and over and over. And this is going to be the equation that governs it. However, in real life, this is where it starts to get a little bit confusing, but I'm going to make it very easy to understand for you. Usually, we don't compound interest every year. Usually, interest is compounded quarterly, which means 4 times a year. There's 4 quarters in a year, 4 quarters in a year, just like there's 4 quarters of a peanut butter and jelly sandwich when you cut it in 4 places, right? Sometimes you even have loans where the interest is compounded monthly or daily or something like that. So we need to talk about what does it mean when you compound something other than annually. So when you have annual compounding, it means every year. That's when you do the calculation. Year number 1, year number 2, that's the only time you get the free money is every year. But when you compound quarterly, you get the free money every quarter. That means 4 times a year. So after 3 months, that's a fourth of the year. Bam, you calculate the free money. Then after 3 more months, bam, you calculate the next amount of free money. Then, and so on and so forth, you do it 4 times a year. That's what it means. But what happens is when you compound quarterly, let's talk about this. Let's just write it down. Compound quarterly. All right, what does it mean? What it means is if I take that annual percentage, remember the annual interest rate in this example here was 8%. That means I get 8% a year, the annual interest rate. But when I compound quarterly, I'm not going to give you 8% every quarter. That's crazy. That's too much free money. What happens is you take the 8% over the year, and since I'm doing it 4 times a year, I just divide that 8% by 4. That's the amount of interest I'm going to give you every quarter. So what happens is I take the 8% that I'm doing on an annual basis, but instead of doing it every year, I'm going to do it every quarter. That means I'm going to take this thing and divide it up into 4 pieces, and I'm going to give you 2% interest as a quarterly growth rate. And again, this is where a lot of students get confused because it is confusing. What happens is if I give you 8% a year, this is easy to understand. Every year, 8%, 8%, 8%. But if I compound it quarterly, I'm not going to give you 8% because that's an annual rate. So I take the 8%, I cut it into 4 pieces. That means it's 2%. I'm going to give you 2% every quarter. That will add up to 8% over the year. But I'm going to do the calculation on the free money every quarter. So I'm going to give you 2% every quarter, 4 times a year. Okay, so then what you would have is that you would have the value at end of the quarter. But remember, I'm doing the calculation now every quarter. Well, actually, the way I want to do it, at the end of Q quarters is going to be equal to P times 1.02 to the power of Q. Make sure you understand that. It's exactly the same formula as this. This was the principal times the interest rate raised to the power of T in years. But now I'm not compounding yearly. I'm compounding a lot more often, quarterly. There's 4 quarters in a year, but still, after Q quarters, I'm going to multiply this balance by 1.02, then times itself 1.02, then times itself 1.02, but I'm going to do it every quarter. Every 3 months, I'm going to do this thing. So it's going to be the exact same table, except the numbers up here are going to be in quarters and not in years. And the interest rate has to be smaller because I'm doing it more often, and you take the annual and you divide by 4 to get that number. Okay, so then you can say the value at the end of T years, when I'm compounding quarterly like this, is going to be equal to the principal times 1.02. Now, instead of Q, you're going to have 4 times T. Why are you going to have 4 times T up here? Why is this 4 times T? Because every year has 4 quarters. So this is where it gets a little confusing. You see, what happens is that I'm really doing an 8% annual growth rate, but I'm going to compound it quarterly. So I'm really going to make it 2%. I'm going to give it to you every quarter. So this principal is time this interest rate every quarter. So at the end of Q quarters, this is what it is. But the difference between this and this is if I want to calculate it in years, like let's say 1 year passes. But in that 1 year, if I put 1 in for T, I've actually compounded 4 times because I'm compounding every quarter. So if I put a T of 1 year, I'm going to have this exponent of 4 because I've done it 4 times. Every 3 months, 4 times. If I put a T of 2 years in there, then I'm going over a long period of time. I've actually compounded this thing 8 times because I've done it 4 times a year. So 1, 2, 3, 4, 5, 6, 7, 8. Every knock is every time I multiply by 1.02 like this. So this equation is the value at the end of T years compounded quarterly. That's why the 4 pops up there. Now, why are we doing all this stuff? Because in every algebra book, or every math book, finance book, whatever, that talks about compound interest, you are going to come across the compound interest formula. And to be honest with you, I thought about just writing this equation down in the beginning and just being done with it. But the problem is if I just throw it at you, you're not going to understand where it comes from. Now I'm going to write it down, and you're going to very quickly understand exactly what it's saying. The compound interest formula goes like this. The value of money that you have some point in the future is equal to the principal, which is how much money I put in to begin with, times a number, 1 plus r over n raised to the power of n times t. Look at how this thing compares with something like this. The 1 plus r over n is what's happening here. Let me write a few more things down here. Okay, the a is the amount of money that I have. The p is the principal. Right? That's easy. The r is the annual interest rate. Right? That's the r. This is the number that goes in there for the annual interest rate as a decimal, expressed as a decimal. And the n means compounded n times per year, right? N times per year. So if I'm compounding quarterly, then I'm going to put a 4 here and so on. And then t is the time in years. All right, this equation actually gives, you can get this and you can get all these other ones from it. So I need to show you where that basically comes from. Okay, let's say that I'm compounding annually. That means once per year, right? And the interest rate is what it is. So let's just say that, let me go ahead and box this actually. Something like this. Actually, do I want to do this on this page? I think I want to do it on the next board. Let's first write down the compound interest formula. The value is the principal 1 plus r over n to the n t. All right, let's say we compound annually, right? So the interest rate was 8%. I can't even write 8. It was 8%, which means the rate that you put into this equation is 0.08. But since I'm compounding annually, remember how it goes. N means it's compounded n times per year. So if I'm only compounding 1 time per year, then n is 1, right? So that means that n is equal to 1. This is what we started the whole lecture with, right? So if all this is true, how would this equation look? The rate is going to be the principal times 1 plus, the rate is 8%, which is 0.08, always put it as a decimal, divided by n times per year. I'm only compounding once, so that's divided by 1, and then raised to the power of n times t. N times t. What does this equation come out to? It's p times, when you divide this, you get 0.08. It's 1.08 to the power of t. This is just t. This thing is exactly what we started the whole lecture with. You see what I mean? Where is it at here? 1.08 times this. So then, yeah, here it is. It's p times 1.08 to the power of t. That's what it is. So all that's happening in this equation, when you look at this in your textbook, a lot of students do not know what this is saying. All this is saying is I'm taking that annual interest rate and I'm dividing it by however many times a year I'm compounding. Because just as I showed you right here, if I'm compounding 4 times a year, I'm not going to give you 8% every 3 months, every 4 times a year. I'm going to only give you 2%. So this division here is telling you what this quarterly growth rate is. Then I'm adding that here to get the new multiplier factor, the 1.02 in this example. And then the exponent is telling me how many compounding periods I have. If I'm putting years in and I'm doing it quarterly, then what's going to happen is I'm going to have 4 compounding periods. So it has to be raised to the power of 4. So let's go over here and see what happens if I compound quarterly. Right? It's the same sort of thing. The rate is 0.08, but now I'm compounding 4 times a year. So I'm compounding where n is equal to 4. It's compounding n times per year. So what it's going to be is the principal times 1 plus, what do I have here? The rate, 0.08. That's the annual rate compounded 4 times a year. This is doing the division, giving me that smaller percentage. And then the exponent here is n times t. This is 4 times t. Notice this is exactly what we said it would be. This is p times 1.02. Then you divide this out here. You get 1.02 to the 4 to the power of 4t. That's exactly what we talked about. Where was it at? Compounded quarterly. Where was it at? Yeah, right here, compounded quarterly. This is if you're just going to talk about it in terms of number of quarters. This is going to be what happens if you talk about it in terms of the number of years. Okay, so when you see the compound interest formula, the way you should read it as follows. The exponent up here has the time variable. That means it's an exponential function that's going to grow like an exponential function. The division here is just because if I'm not compounding annually, I need to figure out what the new rate is that I'm giving you quarterly. So I divide it by the number of compounding periods to get a smaller interest rate. Then this 1 plus ends up giving me the multiplier factor in here. The exponent has to have the number of compounding periods per year times the number of years. So this exponent is just how many compounding periods I have altogether. All right, that's it. That's all you have. So what I want to do is at least work one problem here to give you a little bit of practice. Okay? Here's the problem. You invest $1,000 at an annual rate of 12%, compounded quarterly. Compounded quarterly. There should be a period right here. How long does it take to triple this thing in value? So what you have to do when you're confronted with a compound interest problem is to first write down the compound interest equation and then identify what in the problem you're given, and then the rest of it will fall out. So let's start by doing that. The value of my money in the future is going to be equal to the value of the money that I start with times some factor. The factor is 1 plus whatever the interest rate is, divided by however many compounding periods I have to give me kind of a new lower rate, raised to the power of n times t. This exponent is the total number of compounding periods per year times the number of years. So when you multiply, you get the total number of compounding periods I have. Now in this case, we are given that, that the principal is 1,000. But we're trying to figure out how long it takes to triple in value, so the amount down the road that I care about is 3 times that. It's given to you by telling you it's trying to triple in value. The annual rate, which is always R, is 12%, but you never ever want to put a percentage in a math equation, ever. You never ever 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 put a percentage in like that. You always convert it to a decimal, 0.12. And then it tells you it's compounded quarterly. That means n times per year, so n is equal to 4. So now at this point, we have to go and put everything into this thing. Let's see what it looks like. The amount that I'm going to have down the road is 3,000. The amount that I start with is 1,000, the principal. Inside of here, I have 1 plus the rate, which is 12%, but I never ever want to use this. I always want to do 0.12. I'm dividing it by 4 because I'm actually compounding this 4 times a year. So I'm going to actually have a smaller interest rate that I'm compounding more frequently. Okay? And then the exponent, n is 4 times t, okay? And I'm trying to figure out how many years down the road does it take to do this, okay? So then what happens? I divide by 1,000, and over on the right-hand side, I'm going to have a 3. And then inside of here, it's going to be 1 plus, when you divide this, you're going to get 0.03 to the power of 4t. So what you're going to have when you flip everything over here, a better way to write it is 1.03. When you add these together, you get 1.03. That's kind of like the new effective number you're multiplying by every quarter. To the power of 4t is equal to 3. I just wrote this side on the other and moved the 3 to the other side. This is an exponential equation. We know how to solve exponential equations now. There's several different ways, but the easiest way is to take the logarithm of both sides, right? The logarithm of both sides. Because when I take the log, then I can pull the exponent out. So you can do whatever base log you want, but I'm going to do a base 10 log of 1.03 to the power of 4 times t is equal to the log of 3. Take the logarithm of both sides. Now, why do I do that? Because when I take the log of this, the exponent can come out. 4 times t times the log of 1.03 is equal to the log of 3. So now I can solve for t. So what's going to happen here, let's go up over here, t as an exact number, when I divide by the 4 and I also divide by the log here, it's going to be the log, the base 10 logarithm of 3, divide by 4, divide also by the log of 1.03. So in your calculator, you can go do a base 10 log of 3 and a base 10 log of this, and you know what the number 4 is, so then you can calculate this. So what you're going to have then, what is the base 10 log of 3? You're going to get 0.4771. And then log of 1.03, you'll get 0.0128, like this. And then whenever you do the division, this divided by the multiplication of those two things, you're going to get, when you round the decimals here, 9.3 years. Now, you're tempted to circle this because that's how long it's going to take to triple in value. However, if you actually circle this, I'd probably give you full credit. However, this thing is telling you that the interest is compounded quarterly. That means you only get the money every 3 months. That's when the new calculation happens. It comes into your account every 3 months. But the answer that I said is it's going to triple in value in 9.3 years. But a quarter of a year is actually 9.25. And then the next time I get money is another quarter, which is 9.5. So it's 9.25, then 9.5, then 9.75, then 10 years. That's when I get the money. So I'm not going to actually have triple the money in 9.3 years because you can really only get money at either 9.25 or 9.5. But if I pick 9.25 as the answer, I'm not going to quite have triple the money. I'll have a little bit less. So I'm actually going to say that it's going to be basically in 9.5 years. I think this is the best answer. You could say this is the exact answer, but since it's compounded quarterly, if I wait till 9.5 years, I'm going to have slightly more than triple the value of this money. If I were to wait to just 9.25 years, which is actually closer to this number, I wouldn't quite have triple the value. So I think this is the better answer. So we have covered one of the most important ideas in all of math. Einstein called it the eighth wonder of the world, because if you understand how compound interest works, you can use it to amass great wealth and prosperity for yourself and your family. If you don't understand how it works, then you take out a bunch of credit cards and say, oh, I'll just pay them later. And then 10 years down the road, you have so much crippling debt, you can never, ever get out from under it. So what I want to understand and make sure you understand is that the growth of money like this is not a straight line. It is not a straight line. It is an exponential curve that goes up. Right? And the reason it's an exponential curve that goes up is because when you take a principal and you multiply every year with some multiplier factor that includes your interest rate, what's happening is you're increasing the exponent every year, and that means it's an exponential curve, which means it's going to go up as an exponential. Now that's called an annual interest rate with annual compounding. But oftentimes, interest is not compounded annually, it's compounded quarterly. But I'm still not going to give you that 8% every quarter. I'm going to take that 8%, divide it by 4, and I'm going to give you 2% every quarter. The formula is exactly the same, but the number in here is now smaller, but I'm doing it more often because I'm not doing it every year, I'm doing it 4 times per year. So the exponent is 4 times bigger because I'm doing it 4 times more often. This is what I tried to do in terms of numbers to make you understand what the compound interest formula is doing. Your principal times this multiplier factor. This is the new interest rate that comes from taking the annual rate divided by however times I'm compounding per year. The exponent is, again, how many times I'm compounding per year times the number of years. And that is how you can, if you're doing an annual thing, you get exactly the same equation as we had derived already before. If you're doing a quarterly thing, you get exactly the same equation as we're deriving before. And then, of course, we did our problem where we had to put in the value of money, the value we started with, and backwards calculate. So oftentimes you have to use logarithms to get to the final answer. I would encourage you to watch this video a couple of times, because if I could put one piece of knowledge in people's brains that could help them in their everyday life, it would be the knowledge in this lesson. You don't know how many people out there have no idea how money actually works. And so when you go out and you buy a car or a house that's way more expensive than you can afford, and you're paying that interest on a home that you can't afford, then you may not understand how in deep trouble you can be until much, much later down the line. So I want you to understand, solve these problems, make sure you conquer this and understand it with me. Then go on to the next lesson where we'll continue working compound interest problems dealing with the exponential growth of money.